Hello everyone, welcome to the tutorial of IEEE standards for floating point representation of a number. We have discussed about a number with being positive or negative, taking the MSB 1 or 0 that we have already seen. So let us jump into where we can denote something like a floating point number, like say 22.5 or something like that. So I'll just give you an example of how to convert a floating point number, say for example 35.7. I've given the link below, and I've also included the link in the PPT, so you can directly go to the website where you can find how you can convert with the detailed steps. I'm also going to explain the same thing. So there are a few steps involved here. So if you have 35.7, so you need to consider only 35 in the beginning. So 35, if you look into the slide here, so division is equal to quotient plus remainder. So forget that. So 35 is equal to 35, you are going to divide it by 2. Whatever the remainder, you're going to place it in, and it is shown in 1, shown in blue. So the remainder which is expected here is 1, because 35 divided by 2 is 17 plus the remainder. You're going to take the quotient again here, 17 divided by 2, and you're going to write the rest of the quotient, the new quotient, and the remainder here. New quotient here divided by 2, the third quotient here again, and then the remainder. It goes on. So 35 by 2 is 17 plus 1. So 17 divided by 2, 8 plus 1. So 8 divided by 2, 4 plus 0. So what you are going to do is, now 35 can be represented by 1 0 0 0 1 1, that is from bottom to up. So 35 in decimal can be written as 10 0 0 1 1 in binary, which you have already seen in basic electronics. So if you just go to this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5. 2 to the power 5 is 32, and this is 3 anyway. 32 plus 3 is 35. So this is clear, I believe. And let us go into the conversion of the decimal part. So the decimal part is 0.7. So 0.7 can be expressed in decimal as 0.7 into 2 is equal to 1.4. So just simply extract the 1 here. So 0.4, just after you extract the 1 here, the remaining is 0.4. So 0.4 into 2 is 0.8. So nothing to extract here, that is 0. So let 0.8 be as it is. So 0.8 into 2 is equal to 1.6, extract 1. 0.6 into 2 is 1.2, and so on. So as it goes, it doesn't stop in 12th step. It actually goes much further beyond. So so what you're going to do is, now in the previous one we had taken from bottom to up. Here we are going to take from top to bottom. That is, you are going either way of the decimal part. So now we are going to represent 0.7 as decimal point, and followed by 1011 0011 0011 and so on. So this is what we are going to get as 0.7. So totally we are going to represent 35.7 as this value, that is 35, and this is the 0.7 in binary. So this is what it looks like. This is 37, and this is my 0.7, which I have already shown in the previous slides. Alright, so let us take it as in a exponential form, because I want it in something called as a normalized form. So normalized binary representation of a number can be expressed as 1 point something in the base 2 into 2 to the power an exponent. I'll repeat, 1 point something into 2 to the power something. That something here after the decimal point is called as a mantissa, and I'll represent it as m. And this exponential form is simply called as exponent. So the representation of IEEE, representation through IEEE, can be given in this particular block. That is the first bit, only one bit for signed representation, that is whether it is 0 or 1. I have already said 0 is for positive numbers and 1 is for negative numbers. So if s is 0 it means positive, S is 1 negative. Alright, then next of the 8 bits are representing the E dash, and just mind that E dash is different from E is exponent and E dash is the normalized exponent. M is nothing but the mantissa. This part is the mantissa, that is 0 0 0 1 1 1 0 1 and so on. Alright, so mantissa can be stored up to 23 bits and exponent can be stored up to 8 bits. Alright, so now my actual exponent is 5 here because 2 to the power 5. Alright, so hence E is equal to, that is exponent is equal to E dash minus 127. I will tell you why the 127 is and why do you have to subtract 127. There is a whole different story here, and just understand the fact that I'll go through that in the next video. So during normalization you need to subtract by 127, that is there is a buffer of 127. Simply understand that you need to be sure to express any number given in the most simplest form, and also you need to represent in the in such a way that very minute value should be able to be expressed, that is 0.000001 should be also be expressed, and that is why we are going to take minus 127. Alright, coming back to that later. So understand that whenever you have a 2 to the power 5 here, how did we get the 2 to the power 5? We are just jumping the signals, jumping the decimal point to the left. So 100011 point something can be written as 1 point something into 2 to the power 5, which is very easy to understand. Alright, so once that is understood, 1 point mantissa in the base 2 into 2 to the power exponent can be written as, exponent is 5 and mantissa is nothing but 0001 1101 and the rest of the things. Alright, so 0 means a positive number. I've already said 0 is a positive number here. This is 0 here, don't confuse with this is not sign. Exponent is 8 bits, that is this is the exponent. Mantissa is 23 bits. Alright, so once you understand that, I am going to represent a valued expression for a single precision as 1 point m into 2 to the power e dash minus 127. That is why we have 1 here. This signed bit is what we are going to get it here. So please don't confuse with that. I will come back to that later. E dash is 8-bit signed exponent in excess minus 127 representation. So whenever I am getting a binary digit here in this way, it is nothing but the value can be represented as 1 point mantissa into e to the power e dash minus 127. We have already established what is e dash. E dash is nothing but 127 plus whatever the exponent is, that is 132. So 132 can be represented in this way. Again the same format, 2 to the power 0, 2 to the power 1, 2 to the power 2, that is 4 plus 128, right? So 128 plus 4 is 132. This is how you represent 132. So if it is a positive number, it is 0. This is 132, that is e dash, and rest of the mantissa is written here. So totally you can write this way, that is the exponent and the mantissa. Alright, so 35.7 can be represented as 0 and the exponent along with the mantissa. Right, please understand that the exponent is always whatever the exponent here plus 127 when you are converting from decimal to binary. If it is ulta, that is from the other way around, you need to subtract 127. I will show you that also. So it is easy to understand. Consider this number, that is single precision number. 0, it is positive, so I will write it as plus, and this part, if you can figure out what is this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, that is 8, and 2 to the power 4, 2 to the power 5. 8 plus 2 to the power 5 is 32 plus 5 is 40. So if you consider this as 40 in decimal, so 40 127 minus 40, that is you are subtracting 40 minus 127, you are going to get 87. So this is the exponent. I'll repeat again: 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, that is 8. 2 to the power 3 is 8, and next is 2 to the power 5. 32 plus 8 is 40. 40 minus 127, excess 127 is 87, that is a negative 87. So 2 to the power minus 87. What are you going to do with the mantissa? You are going to write the mantissa after the decimal point as it is, and since it is a normalized form, it is 1 point mantissa. Remember that it is always plus or minus 1 point mantissa into 2 to the power e dash minus 127. So this we are going to convert from binary to decimal. That is why we are subtracting 127. Here we are going to convert from decimal to binary. That is, we are going to add 127. E dash is equal to 127 plus 5. I hope this is clear. So let us understand IEEE standards for floating point numbers with the normalized form and without the normalized form.